Let's move on, and I want to talk about these last few notions here, namely this notion called correlation. Right, so we're going to talk about that, and I'm going to motivate it with a couple of pictures. So hopefully you guys can see this. I'm going to draw a few pictures. My volume is down. I'm going to draw a few pictures, and take a look at what you think you see here. I'm going to draw 3 scatter plots. 1, 2, 3. Now I'm going to draw, let's see here, pretty much the dots in a straight line, sort of going up, right? I'm going to connect these. So that's going to be the regression line through those points. I don't know what the data are, right? I'm just assuming that when you plot it, it's going to look like this. So that's one of them. Here's another one. And you can just kind of put them sort of how I have them, but just something like that. And let's say the regression line looks like this. And then finally, something that looks like this. Just kind of really sporadic dots. Really sporadic dots. And let's say that regression line looks something like that. If you look at those green dots in comparison to the line, you'll notice some interesting phenomena. In particular, with the first one here. Now, I don't know if you will ever have data like this, right? So I don't know what this study is, but looking at the scatter plot, do you see how those green dots fit perfectly on that regression line there? So it's like a sense of tightness. I don't know if you guys watch football or whatever, but sometimes they do this thing called huddle, where they sort of get together, sort of talk amongst each other, right? So these are kind of like really huddling over the line almost perfectly. They're touching the line perfectly. Now let's look here. These dots are different. They're not as close to the line, and they're actually going in a different direction. If you look at this line here, you see how it's like going downward, kind of like a negative slope vibe, right? Now these are not as close to the line, but they're not too spread out either, like these. See how these dots here just kind of are seeming like no sporadic, they seem very sporadic, nothing really close to each other, whatever. And so now this line here, what summarizes that trend, if you calculate the regression line going through that long process, finding slope and y-intercept, this line kind of ends up being like this. So this notion of correlation has to do with, in general, conceptually, sort of how close are the dots to the line, right? Now, generally when we measure correlation, and after this we're going to write a formal definition, but I'd at least like for us to see it, we use the value of R. So we say R equals something. When I say R equals something, that's telling me, it's giving me a sense of how the dots relate to the line here. Now this is almost like a perfect fit. Now if you ever find data like this in the real world, I'll give you $1 million, because generally data just falls where it does. Not necessarily directly on the line, even if it's off a little bit. So this is the case here. It's almost perfect correlation. So we're going to say R equals 1. R equals 1 means like a perfect kind of correlation, right? All the dots literally are on that particular line. Now go here. Look at this notion of R. Okay, so it's not 1 because the dots are not on it. And it's going in a downward direction. So here, I'm going to say R equals a negative, because it has like a negative trend going downward. Negative, I don't know, let's say 0. And I'm totally picking this up. Let's say 0.6. 0.6. Because what we're going to find out with correlation is going to have an upper limit and a lower limit. R is always going to be between two numbers, and we're going to figure out what those two numbers are. Now look here. If I had to say R equals, like I really can sense no pattern. No upward pattern, no downward pattern. Those dots just seem to be doing whatever they want to do, right? So in this case right here, a possible value for R in this situation could be 0, because those dots don't seem to be congregating around that line in any kind of measurable or conceptual kind of way. So having looked at this right here, even without going into a definition, what range of values do you think R must be between this number and that number? Anybody want to offer a guess? R can only be between two values. It'll never go up here and it'll never go. Okay, almost, Lydia, almost, right? But see here how this R here is a negative 0.6? So I have to force myself to go the other way too. Good, good, there you go, very good, right? So when you deal with correlation, just in general, in terms of the picture, this is R equals 1, and then as a matter of fact, on your own paper, draw what you think corresponds to R equals negative 1. Draw a picture, draw some dots, draw a line, draw something that you think would look like R equals a negative 1. R equals a negative 1. So they would have to fit perfectly on that line, right? But just going in a negative direction, something like this. See that? Very good, very good. So that would be a case where R equals negative 1. Okay, so if you're talking to somebody who took a stat class, they say, oh yes, I did this study and I was doing a correlation and my correlation was 1.5. Just walk the other way because they don't know what they're talking about, right? It only can be between negative 1 and 1, right? And so this is a general picture. So let's write a definition for correlation and let's see what purpose it serves in terms of the actual data. And it has to do with how comfortable or how reliable or how strongly you feel about that data predicting other values. So I'm going to say this. I'm going to say definition. I'm going to say definition. Correlation is a statistical measure. Correlation is a statistical measure of the relationship between two random, this pen is giving out, random variables. I'm going to repeat this. Correlation is a statistical measure of the relationship between two random variables. Okay, so when I had this drawing that was up here, say for example, I don't know what the data represents, but I'll make up something. So let's say like this is X, right? This is X and this is Y. Now notice here, I'm just going to put this back up here, just very. So notice this. So this looks like a negative relationship, even without looking at the regression line. You see how it's kind of going downward. So think of a situation in real life where as X increases, see how I'm going more and more and more in this way? What is Y doing? Y is decreasing. See, this is Y. As X increases, you see how Y is decreasing in terms of the dots? See how they keep going down, down, down? So let's see, what kind of relationship in real life has a negative relationship? As something increases, something decreases. As something increases, something decreases. Well, you have a number of things. Increases in absences. Let's keep it real, right? As absences increase, generally scores decrease. I mean, in general, and unless you're like a brainiac or something. Spending goes up. Money. Okay, yeah, very good, right? So the more money I spend, the less money you have in the bank. Kind of left over. Very, very good. So you kind of see, like, for example, so between two random variables, so this could be spending, and then this could be in bank, right? So as this increases, this is like decreasing. So the correlation is looking at the relationship between two variables, spending money, whatever these two variables are, is giving you a sense of how related they are. And it gives you a sense of how reliable, and so I'm going to write this as well. Let's say provides a sense of, provides a sense of how reliable the prediction, how reliable the prediction line is. How reliable the prediction line is. Now, in different courses, you can, it'll tell you different chunks of, we said between -1 and 1. It'll tell you which one generally is a strong correlation, but statisticians can't really agree per se on the actual cutoff. But in general, when they say if R is greater than 0.8, or if R is less than -0.8, we say there's a strong relationship between these two variables here. Amount of money you spend and money, or whatever the two variables are, right? So you can kind of imagine this picture, R equals 0.8. So the closer it gets to 1, the closer those lines come to touching. But watch this though. Just because you have a negative relationship doesn't mean that it's weak, right? R equaling 1 and R equaling -1 are just as strong. Right? So I don't want you to view it when it has a negative correlation that is weak. It's just a strong negative correlation, right? So if R is greater than 0.1 or R is less than if R is greater than 0.8 and R is less than -0.8, we say it's strong. So the closer it gets to that 0, remember that picture with 0 where the points just look like they were everywhere? Then that's when we say it's weak, right? So from like 0 to maybe 0.5, and then you get different people who say moderately weak, maybe 0.5 to 0.8. I'm not going to worry about that. The only thing I'm really concerned about your knowing is, if I give you a scatter plot, can you kind of roughly see what R should be, right? So if you have all the dots on one line, I know R is not 0, okay? And that just goes like, say for example, when I'm going to show you in Excel how to find this number, but we came up with, for example, a Weiss of L equals something. I forget what it was. I think the problem, the GPA problem, I think we got -0.01x plus, I forget what you guys told me, like 3.7 or something like that, I forget. And let's say, for example, I want you to predict a GPA or predict something when I give you this particular X value. I forgot what X represented in that particular problem. So how comfortable do I feel with the answer that it gives me? Of course, I can always get a regression line, an equation, but when I put the value in for X and I get a Y out, how reliable is that answer? Or how confident do I feel that answer is a good answer when I'm predicting? Well, I have to look at the value of R to figure out, okay? And we're going to look at Excel in a second to sort of see how we get that value out. But I just want to give you heads up, first of all, on what correlation means and how you're able to see it in Excel in a second. Now, this is going to be on page, I had the page, just 1 second. If you want to take a look at this, on page 305. Look at page 305. And it discusses R as something called the linear correlation coefficient. That's another term they have for it. But notice there on page 305, the bottom there in the little purple or the blue little box, they define correlation. They see it's between -1 and 1, right? They don't really have that many pictures, but, on page 308, yeah. Look at page 308. You see those 3 pictures right there, like in the middle of the table there? Well, that's in general. And I don't know about that R equals 0.9. That doesn't really seem, because if R equals 1, but anyway. But that's a general idea or notion, page 308 and page 305. Now we also have this measure called the coefficient of determination. So I'm going to do that, and then we're going to turn to Excel to figure out how to do this stuff on Excel. So we have correlation, and then we have coefficient of determination. So these are the last topics that was on the review that we mentioned earlier today. Coefficient of determination. Now, let's write a definition here. Let's say definition. I don't feel like writing all this again, so I'm just going to say COD, the coefficient of determination. And here I'm going to write R squared. So R squared is just the statistical symbol that we use for coefficient of determination. Now, for correlation, we just use R. But for coefficient of determination, we're just going to use R squared. So that's why I put it in parentheses. Is the proportion or percentage of the variation. Okay, so the coefficient of determination is the proportion, and you can use the word percentage there, of the variation in Y that is explained by the variation in X. Okay? And let's say is similar to the value of R. Right? So in other words, both of these statistics give you a sense of how one variable relates to the other, but they just present it in different ways. So say, for example, we just talked about R. And when you talk about R, which is the correlation coefficient, that gives you a sense of not only how close or not close the two variables are, but in what direction, whether it's a positive correlation or a negative correlation. But here, do you see how, like, when we square R, let's say if our R, I don't know, let's imagine that we do the calculations and our R ends up being 0.9 and a negative 0.9. So literally, when you square this value of R, like in this case, I think you get R squared. I think it's 0.81, if I'm not mistaken. But what is it also here? It's also 0.81. Because when you square a negative, it disappears, right? So when we look at R squared, and we're going to write an example of how you would write that answer. When you look at R squared, it's still telling you the relationship between those two variables. But number one, now you don't know whether it's a negative or positive relationship, right? Because the negative disappeared, right? But it also tells you how much of the variation is explained by a variable outside of X. Yes.
Can you please read the definition one more time, just because it's hard to read?
Oh, okay, yeah. So we're going to say the COD, or the coefficient of determination, and then I put R squared, is the proportion of the variation in Y that is explained by the variation in X. And I said it's similar to the value of R. So essentially, the answer to coefficient of determination will always be in a percentage. Okay? Well, how do I get that percent? I square R, whatever R is. Now, we're not going to go over in class how to calculate R, but I can show you a formula for how to calculate it in the book there, but we aren't going to waste time in class calculating R. It's similar to how we calculate slope, right? All those summations and it's just really crazy. But if we calculate it, for example, we get R equals 0.9, well, I square that in the calculator, square that, and then how do I change a decimal to a percentage? Like once I get to 0.81, that becomes what as a percentage? What do I do? I basically decimal twice to the right or multiply by 100. Is that what you're going to say, Ashley?
Yeah, I was going to say 81%.
Yeah. So it shows how to go from R to R squared. And so essentially I just multiply by 100 or move the decimal twice to the right. So in this case, my coefficient of determination is 81%. Well, what does that have to do with the real life world of the problem? Okay, and we're going to figure out how to say that. Should I tell you now? Yeah, I'm going to figure out how to say that. And I'm going to go back to the data set foot traffic and sales. Now, I don't know exactly what that R squared is, but let's imagine that it's 81%. We're going to say how to say that, right? And normally people just kind of use this when they are undergoing a study and they have to write in their report something about coefficient of determination because they want to be able to tell people what, how one variable relates to the other one. So this is the way it could be written. Now, this is variation in Y that is explained by variation in X. So imagine our Y is sales and our X is foot traffic. And let's imagine we come up with the R squared value of 81%. It would go something like this. The proportion or the percentage let me start over. Sorry about that. So this is how we would say it. You have this 81% here. Yes. 81% of the variation in sales, or whatever your Y is in that problem, 81% of the variation in sales is explained by the variation in foot traffic. Again, I'm only offering this explanation based on our assuming that this R came from another data set that we were looking at. So here's the 81%, which is pretty good. Yeah.
Does the EG mean like example or
Yeah. Sorry about that. Yes, I could say EX or example. Yeah. So okay, so here's what this is saying without getting too deep or whatever, and it's going to be better once we look at it in Excel. So once you figure out what R squared is in the problem, and you're going to be able to just look at that number in Excel, we're saying 81% of the variation in Y, and we're going to assume we're talking about sales, the other problem, is explained by the variation in foot traffic, or X. Now, what does that mean? The closer, like when we talk about R, we said it's between -1 and 1. Sort of like perfect on the positive end and perfect on the negative end. What is 1 as a percentage? If you think about 1 as a decimal, like we said 0.81, the percent was 81%. What is the percent for if I say just 1 as a decimal? What percentage is attached to that? 0.81. Yeah, good. Yeah, Jaylene, you went the other way. So go to the right. Yeah, so we're going to say 100%. So you got, in the case of R, perfection is 1 or -1. Well, multiply those by 100 and move the decimal twice to the right, that's 100%. So in the world of coefficient of determination, the closer you get to 100%, then the stronger that relationship is. And look here, 81% of the variation in sales is explained by foot traffic. So then, here's a trick question. Listen carefully. If 81% of the variation in sales is explained by the variation in foot traffic, then what percent of the variation in sales is explained by sources other than foot traffic? Okay. Lydia, how do you get that? You just don't want to talk, do you? Okay, no, you're right. You're right.
Yeah, I just subtracted 100% from 81.
Yeah, yeah, okay, no, that's fine. Yeah, you're exactly right. Because see, did you guys hear my question? My question was, if 81% of the variation in sales is explained by what we're studying, which is foot traffic, then how much of the remaining variation comes from sources outside of foot traffic? You're exactly right. We're saying 100 minus 81, which is kind of a good thing, right? Because in other words, the closer that number is to 100, like the 81%, the closer that number is to 100, then that's saying, hey, this relationship is pretty tight. It's pretty strong. There's not that much variation outside of what I'm studying, right? So the closer that number is to 100, it's almost like the closer the R value is getting to 1, right? Or negative 1, right? So that's a general idea. So if we can get close to 100% right here, that's saying we have a strong correlation, or we feel pretty confident when we have to put in a number to predict from the regression line. We feel pretty confident at whatever that answer is because there's a strong correlation between those two variables. Okay, so I don't know if that makes sense, but that's in general what we're looking at. So just kind of be able to know how to say that, right? Coefficient of determination.